Derivative of a tensor. A natural question arises that if I make derivative of component of a tensor, do I get a component of a tensor? And the answer of this question is no in general, and we will show that by an example. If I take, for example, Vm, which is covariant tensor of ring 1, and this covariant tensor, which is vector here, is constant. If I suppose I'm dealing with flat, then I can choose Cartesian coordinate. Then dVm over dxn equals 0. But what happens if I may choose, I am not in flat, I need to choose other curvilinear coordinate. Then dVm over dx prime n not equal 0 in this case. Why? It's natural, because the component of a vector not only depends on the orientation and magnitude of a vector, as we usually use to think in Euclidean geometry. But in differential geometry, where things are not necessarily flat, then I need to introduce non-Cartesian coordinate, and in this case is the vector also. The component of vector also depends on the orientation of the axis I choose, which is varies from point to point in this. So that tells us the derivative of component of a tensor doesn't behave as a tensor. To introduce a tool that I make derivative of component of a tensor and I get tensor, or I get component of another tensor, then I should introduce what's so-called covariant derivative. And the word covariant is doesn't mean anything, it's just a name. Doesn't relate it to covariant and contravariant, which we talked previously. So to show that, we need to take an example, and let's suppose that I have a vector, covariant tensor of ring 1, which is vector, and then make derivative of it with respect to the position, and then I suppose that I get a tensor. So Tmn is equal to dVmx over dxn, and let's suppose that Tmn behave as a tensor. The fact that behave as a tensor implies that its transformation rule follow the specific Tmny equal dxr over dyn multiplied by dxs over dyn multiplied by trsx. So, but I know that trs in x component and in x coordinate is dvr over dxs. So by injecting it in the formula, I can get Tmn is equal dxr over dym multiplied by dxs over dyn multiplied by dvr over dxs. The question here, is this equal or not dvmy over dyn? What is dvmy over dyn? I inject Vm by its component. Vm component is dxr over dym multiplied by vrx. So now I have derivation of both, of multiplication of two terms. The first is dxr over dym and the second is vr. So naturally I will get two terms, and this is the problem here, because in black bracket we have derivative of product. So I have two terms. The first term is what I will get if I expected it as a tensor, which is dxr over dym multiplied by dvr over dyn, and beside that I have another term, which is d square xr over dym dyn multiplied by vrx. This new term is called connection, and we use gamma as a symbol, and gamma mnr. I have three indexes, m, r, mn, and r also. So this term physically express the relationship between the axes when we move from place to place. So how the axis or how the coordinate it changed from point to point. And here it is just we are talking in very special case, and this is not the formula of gamma in general case, and we will conclude how we can find gamma in general case. So to derive a tensor and get another tensor, we need to introduce this new tool, which is covariant derivative. And covariant derivative of a tensor of a vector, for example, Vm, is its normal derivative, or dVm over dyn, plus a gamma, Christopher symbol, also called Christopher symbol or gamma or connection. Gamma in Mr, Vr, where R is the summing dummy index, equal Tmn. Now I have Tmn. I am sure that I have this as a tensor and not as previously. And the usual notation for this is gamma n Vm. For instance, if I take covariant tensor of ring 2, I have two indices, so Tmn, and make covariant derivative of this tensor, then delta b or nebula p Tmn is equal to the normal derivative, which is Tmn over dyp. And now I make a trick. I forget about n, for example, and I choose Tm, which is gamma Pm R Trn, plus now I make I forget about m, and I get plus gamma B N R Trm. And this is the covariant derivative of tensor of covariant tensor of ring 2. And later we will see other example, important and basic example about covariant derivative. Covariant derivative of a metric, for example. What is the covariant derivative of a metric? By definition, the covariant derivative of a metric is equal 0. That physically means that this my physical tool of measuring the distance between 2 points should be the same, doesn't change from point to point. Otherwise, I have a not good metric. So it is not fair metric. So it is property of metric that its covariant derivative, it should be equal to 0. That implies if I just inject because it's covariant of order 2, the metric is covariant tensor of order 2, then just by injecting by the previous equation in green, it was surrounded by green, I will get equation, which this equation, by solving it, it's nasty way to, there is lots of calculation behind the solution, but the solution could be found and could be finally given by gamma BCA equal half GRD above, multiplied by the 3 term, the first the sum of dg dc over dxb plus dg db over dxc minus dg bc over dxd. Gamma, as I told previously, it called connection and also Christopher symbol, and it plays an important role in gravity and in gravity in general relativity, as we will see in few lines. Other example of covariant derivative of tensor type 1,0 it is like contravariant. It's of type 1,0, so it's contravariant of ring 1. Also, it is a similar way, dvn over dym plus gamma mrn vr. So the position of the summing vector, one of them above, one of them down, and this is this is how I call it covariant derivative of a tensor type 1, 0. One of very important example is tangent vector. If I need to make the covariant derivative of tangent vector. To introduce tangent vector, I need to introduce space, for example, arbitrary space, and I can take curve inside it. And there is field. And let's find how the tangent vector of this curve change from point to point. That means I need to make a kind of derivation. And before that, along this curve, I need to make parameterization, ds, for example. And then inject this, the tangent vector. The tangent vector is given, Vn is given by dyn over ds. So injecting this dyn over ds in the previous formula, what I will find that I have one of the derivative dyn will goes with dyn down, so I will get the derivative d square yn over ds square plus gamma mrn dym over ds dy multiplied by dyr over ds. And this is tensor because we take covariant derivative. So if the curve is straight line, and I'm using in Cartesian coordinate, I mean there is flat, then this covariant derivative is 0. But in more general cases, if there is no flat, there is arbitrary curvilinear coordinate, the covariant derivative of a tangent vector along certain curve is equal 0. That means this curve only if this curve is what so-called geodesics. Geodesics, that means the covariant derivative of tangent vector along this curve is 0. What is the physics behind this? Why it's important? In the same formula, which is in black rectangle, that means that this is equal to 0. That means the second derivative of, for example, if I take s is equal to time, time, then the second derivative of dyn over dt square is equal to minus gamma mrn dym over dt by dyn over dt. So the first part, the second derivative with respect to time, which is acceleration, I just need to multiply by the mass in order to get force. So firstly, the second hand of the equation expresses somehow a kind of force. And since the Christopher symbol, the gamma, actually contains the covariant derivative of metric with respect to the position. So and this is expressed more or less a gravitation force in Newtonian sense. So the orbit of the particle under gravitational field acting on it they will follow geodesics. And this things, the right hand side of the equation, the previous equation, is express the gravitational force.